All right, everybody. It is 10 o'clock on the dot. My name is Madeline Landis, and I'm a sales engineer at Long here at the Denver office. Super excited to have you all today. We have Taryn from Strobic Air. He is going to be presenting this morning on sustainable lab design and how you can use the Strobic Air technology to really channel in and dial in the most sustainable design for your labs. So thank you all for joining. As always, I will announce a winner at the end, but appreciate everybody, and I'm going to let Taryn fire away.
All right, Madeline, thanks so much. Thanks to everybody for being on this morning. I appreciate the opportunity to talk to you today. Today's all going to be about sustainable design of efficient laboratory exhaust systems, like Madeline was saying. And what that means is, I'm just going to read this. We are looking to gain an understanding of sustainable laboratory exhaust design principles with a focus on high plume, high dilution products like Strobic that ensure compliance with safety and performance standards are being met while maximizing the efficiency of the system. So when we think about labs, right, labs often have high volumetric flow rates for safety, which means huge volumes of conditioned air being exhausted outdoors. So exhaust fans typically could run 24/7 in many facilities, which what that's going to do is it's going to create a very energy intensive environment. So sustainable design aims to reduce fan energy, heating and cooling load, and overall carbon footprint, all while maintaining safety and compliance that's going to be required in these critical environments. So when we talk about designing sustainable lab exhausts, right, the first step is to right-size the system. So far too often, these systems are over-designed to meet these theoretical maximums, right? So instead, what we really want to do is we want to design around actual diversified demand while still accounting for those peak demand building spikes. That's going to help us avoid wasted capacity, unnecessary energy use, and make sure that we have the right-sized equipment for our application. So next, we're going to look at the motors, the fan configurations, and the controls. So using premium efficiency motors in an efficient and reliable true direct drive configuration like Strobic Air does, paired with VFDs, that's going to allow us to dynamically match fan speed with real-time building needs. Furthermore, options like the Safe Controller, which is a product that we offer, we can integrate intelligent controls logic to maintain safety while optimizing efficiency. All right, so that's going to mean that we're making the best corrections possible rather than just guessing, right? So the concept relatively simple. When you think about fan is operating at full speed, bypass dampers are open, and there's room in the outlet velocity of that system for turn down, the intelligent controls logic tells us exactly how much, right? So it's not just a guess of turn down the fan, close the dampers. It's a precise correction to really optimize that system. Another big piece is energy recovery, right? It's a big optimization opportunity, especially exhaust heavy buildings in harsher climates. So if we use technologies like, your glycol runaround loops, we're going to be able to recover significant heating and cooling energy loads without compromising lab safety with no risk of cross-contamination. Finally, when I say long life, low maintenance systems, system material plays a key role in the reduction of embodied carbon over time. Right, so durable, corrosion-resistant options like Strobic offers in terms of FRP or properly coated metals, it's going to extend the life, reduce the need for replacements, and actually lower embodied carbon over time. So that combination of efficiency, durability, energy recovery, all while understanding the right size design, that's really what sustainable laboratory design is all about. So when we talk about optimizing fan size and quantity, a key feature of sustainable lab design is the ability of the system to be able to handle variable flow and pressure. Different labs, hoods, and processes rarely demand the same airflow at the same time. And by designing systems that can efficiently manage these fluctuations, we can maintain safety, all while avoiding wasted energy. And this is going to tie directly into turn down capability, right? So with the right fan technology, the right size design, we can scale airflow up and down as the building demand changes. And that flexibility is absolutely critical, right? It means we're not running fans at max speed when only part of the system is in use, which is going to translate to a major energy savings. Another advantage we have is the ability to combine smaller exhaust streams into a single manifolded system, right? So instead of running multiple independent fans, we can integrate them into one multi-fan array. What this is going to do, not only is it going to lower the static load, but it's going to reduce your equipment cost and create a more consistent plume dispersion. Finally, and this is no secret of common knowledge, but by designing to reduce the bypass airflow, we're going to ensure that every cubic foot of conditioned air leaving the lab space is serving an actual purpose. So minimization of the bypass air improves overall efficiency, and it's also going to help maintain the precisest control of the lab ventilation. So I spoke to this in the previous slide, but when we talk about diversity, we mean recognizing that not every lab space, fume hood, or exhaust device will be operating its maximum flow at the same time. So in practice, and the image here demonstrates this, usage varies throughout the day, right? Some hoods are closed, some labs are unoccupied, and some processes are only running intermittently. So what were to happen if we were to size our exhaust and supply systems is if every single piece of equipment was at full load 24/7, we're going to end up with a massive over-design. It's going to be larger fans, oversized ductwork, higher energy costs, even though the actual demand, the true diversified demand, could be far less. So applying these diversity factors, if you will, that allows us to right size the system to handle what's going to be a more realistic peak condition, as well as a realistic demand diversity. A couple benefits. First, it reduces capital costs, right? Smaller fans, motors, ducts means a lower initial construction cost. But second, and I would argue more importantly, is it's going to translate to a reduction in ongoing energy use because the system is designed around a true demand rather than a worst case scenario that infrequently happens, right? So we got a few ways in which control takes place, staging bypass air, modulation of fan speed. Just to give some backstory, in a lot of traditional lab exhaust systems, right, these fans have a fixed speed and flow that they need to run at to stay stable and to keep the exhaust plume safely diluted. Now, the problem is the lab's actual demand often drops below that level. Maybe there's fewer fume hoods or certain spaces are not in use, right? And to deal with that mismatch in a constant speed setting, the system brings in or injects what's called bypass air. So basically, it's pulling in ambient air, mixing with the exhaust stream so the fans can continue to keep running at their set speed while concurrently not overpressurizing the space. And it works. I mean, it certainly does work as a sequence, but here's the catch. All that bypass air is clean ambient air that you are processing through the fan system, and that's going to translate to wasted energy. So that's why when I talk about systems like the Strobic Air Safe system, they're designed to reduce or even eliminate bypass air when feasible. So with the variable speed fan, smart control logic, and the appropriate fan sizing, we can keep that plume safe. The effective plume rise continues to exist, but we're not wasting with the injection of too much bypass air. So it's safer, smarter, it's a lot more efficient. So when we go to control through VFD, control through fan modulation, right? The Strobic Safe Controller is designed to prioritize safety first and foremost as a life-critical device, but it also has the logic to consider efficiency in your lab exhaust system. So traditionally, like I was saying, with fans running at fixed speeds and relying heavily on bypass air, that meant a lot of wasted energy. With the Safe Controller, the system constantly monitors all these real-time conditions like building pressure, outlet velocity, and other inputs, and it makes these precise adjustments to fan speed safely and dynamically using the drives and modulation of the damper. It's all against the proprietary sequence of the Safe Controller. So when demand is low, the controller slows the fans within the safe limitations of the system. And when conditions change, it ramps them back up, eliminates bypass flow, and maintains that proper plume dispersion safety. Real big advantage here is the controller, it's going to minimize or eliminate the need for bypass air when feasible, right? So instead of exhausting extra ambient air, it uses the smart system modulation to get the same safe plume height with less airflow. So that's going to result in lower fan horsepower, reduced heating and cooling loads, and it's going to translate to an overall energy savings. It's a good example, right? When I talk about, operational diversity, and this affords a chance to energize, to de-energize, to turn down as appropriate, and just really contributes to greater operational diversity versus a single fan array. So heat recovery, I'd mentioned that a few slides back. And when we talk about laboratory design, one of the biggest challenges we're going to face is energy use, right? And I've already covered that labs can be some of the most energy intensive buildings out there. It's driven heavily by the exhaust system. So the issue lies in the exhaust air is conditioned air. It's already been heated, cooled, right, to make that space comfortable. And we're going to throw it right outside. So without any recovery, you're dumping energy and money right out the stack. So that's where heat recovery is going to come into play, and a properly designed heat recovery system that allows us to capture a large portion of that heating or cooling energy from the exhaust stream and transfer that back into the incoming fresh air. Right, the two streams don't mix. This is a runaround loop, so safety always comes first, but energy can still be exchanged through these systems. Now, benefits are big, right? You're going to reduce the load on your mechanical systems. You're going to reduce your heating and cooling load, which is going to translate to a reduction in your utility bills. And second, you're going to reduce the building's carbon footprint, right? So to meet those sustainability goals and green building standards. And we got to consider, because these laboratories oftentimes are running, 20 plus hours a day, 7 days a week. These savings are substantial, right? They're not seasonal, and they're going to add up almost every day of the year. So energy recovery, heat recoveries as provided by Strobic, we offer this turnkey solution. It's not just a nice to have when we think about sustainable lab design. It's almost essential, right? It's about smarter energy use, safe buildings, and more sustainable operations. So final point that I want to get into, when we talk about sustainable lab systems, it's not just about saving energy on day one. It's about creating systems that remain efficient, reliable, and cost-effective throughout the entire life cycle of the product. So the low maintenance requirements with fewer touch points, it's a key part of that, right? And that's what Strobic's all about. One of the simplest maintenance protocols in the industry. And systems that require fewer interventions, they reduce downtime, they cut labor cost. It's not just good for the bottom line, it's good for sustainability, right? Fewer replacement parts equates to less waste over time. Durability is going to go hand in hand with this. These are 24/7 operations typically, and equipment's under constant demand. So durable systems that are built to withstand the harsh environmental and operational conditions and to deliver that consistent performance year after year is directly going to contribute to sustainability. Investing in durable systems, it means less frequent replacements. It's reducing your embodied carbon and long-term operational costs over time. And finally, the Strobic air vibration standard contributes to longevity like none other, right? It's the half mil peak to peak displacement rating for each and every one of our tri-stacks, which again, it's reduced mechanical wear and tear, less vibration. That's going to translate to sustainability in terms of a longer lasting system. Finally, we don't just make that promise, but we stand behind these products, right? So in terms of sustainability, the longevity, we're going to provide a warranty that far exceeds the industry standards, right? It's going to cut premature replacements. It's building to the right standard in the first place, and providing a reliable system that's going to run with less downtime, fewer repairs, and contribute to operational efficiency and overall resiliency. So thank you so much. I do appreciate your time today. Thank you, Madeline.
Definitely do that so you can get your spa finder, your tabletop kettle corn, or your bacon soda And then definitely if anybody has any questions about Strobic, please let anyone at Long know. And thanks so much for joining. Have a great Thursday.
Thank you.
Thanks, Darren.